Hi, my name is Ramesh Dungana. I teach physics at the University of Colorado, Denver. I'm glad you stopped by. Nature is full of motion. In these pictures, we see some example of motion. People rowing boats, or bees pollinating flowers and gathering honey. Our body is a complicated engine. Lots and lots of kind of motion happening inside our body. We describe all kinds of motion using few physical quantities, such as displacement, velocity, acceleration. In this video, I define such quantity and more specifically focus on differentiating between distance and displacement, velocity and speed. Are you ready? Let's go. Let's start by asking a simple question. What is your current position? You may say, hey, I'm sitting on a chair. Okay, you are sitting on the chair. But what is your position? To describe a position, we need some reference point. If you choose the chair as reference point, your position is 0. If you choose door somewhere around here in the room as a reference point, your position is not 0. Now let's ask another question to make this thing more clear. What is the position of this ball? You may ask, position with respect to what? We assign a reference point or origin to describe a position. Now I can measure and tell the ball is, say, 1 meter to the right from the origin. Position is a vector quantity. A vector needs both value and direction to completely describe it. We draw an arrow to represent a vector. In this sketch, the arrow denoted by xi is the initial position vector. Length of this arrow is related to the value of the vector, and arrowhead is related to the direction. Initial position in physics is when you start measuring the position. The object could be at rest or already moving when you start timing the motion. Now the ball starts moving. Whenever you decide to make another measurement, it has a new position. The new position is final position. And again, this also being a position vector, it is represented by drawing an arrow starting from the origin to the final position. So this is final position vector denoted by xf, and this is initial position vector denoted by xi in this case. The time ti corresponding to the initial position measurement is the initial time. We can denote initial time as ti. The time related to the final position is, say, tf. When we subtract initial position from final position, we get displacement. Displacement is a vector. Therefore, we draw an arrow starting from initial position to final position to represent the displacement in that direction. The delta always means final minus initial. Therefore, delta x is final position minus initial position. More specifically, delta x is displacement towards the chosen x direction from initial position to the final position. Similarly, delta t means final time minus initial time, or simply time interval. Time does not need direction to describe it. For example, we don't need to say 2 seconds to the left or right. Simply saying or writing time is 2 seconds is enough to describe the time. A quantity that does not need direction to completely describe it is called scalar quantity. Therefore, time is an example of a scalar quantity. If we decide to choose origin at the initial position, the initial position becomes 0. Let's copy the origin down here for 0 initial position. In this sketch, I am marking initial position right at the origin, labeled as xi equal to 0. Thus, the displacement delta x, which is final position minus initial position, becomes final position minus 0. Notice I plugged 0 for xi. This is simply xf. Since there are no two subscripts anymore, we might simply write x. So delta x, or the displacement, is simply x when we don't have initial. So final simply is x. Similarly, when initial time is 0, you can write time interval simply as time, t. You can set initial time to 0 by setting up your watch or stopwatch 0 before starting the time measurement. Thus, the time interval is simply t. So, when you see time interval written simply as a t, it is a special case when we are assuming the initial time was 0. Here is a quick check for you. Go ahead, please read the question and come up with the answer. So we'll talk about displacement versus distance more in next slide. You can come back and check this slide after you go through that one if you still have question about it. Now let's get to one main question. Are displacement and distance same? The short answer is no. You may ask, how so? We package two informations in displacement but only one in distance. We need to include both value and direction in displacement, but distance has only value. For example, the ball moves say 2 meters from initial position to final position. Without knowing which way it went, we only know the distance. The odometer in your car records the distance, not displacement, because it does not record the direction. We can mention direction by real physical direction, like to the right, to the left, up, down, east, west, etc. In this example, the displacement of the ball is 2 meters to the right. When we use vectors in an equation, we assign either positive or negative sign for the direction. Here I am saying displacement is positive 2 meters. Because displacement is 2 meters to the right. So that means I am assuming that right is positive. By writing positive sign, we are telling the direction of the displacement. 2 meters is value and positive sign is direction. However, the same displacement becomes negative 2 meters when we assume right as a negative. The value is still 2 meters, but since we are assuming right is negative and the displacement is to the right, it must be negative. Remember, the sign means direction for the vector. So negative sign is to the right. When you assume negative is to the right instead of positive to the right. Depending on what we choose, it could be positive or negative. Therefore, it is very important that you pick a sign for a direction. Like right is positive or left is positive before you use vectors in the equation. You will see an example in next slide. On the other hand, when we say distance, we are leaving the direction information. To find the distance, you simply measure the path length, how far it went from here to here. In this example, length of the arrow is 2 meters. Therefore, distance is simply 2 meters. And for that, we don't need to write positive or negative sign. Or you can say it is always positive. Thus, when an object is moving along a straight line, the distance is the value of the displacement. Value can be same when it does not reverse the direction, just keeps moving in the same direction. Okay, then what happens when object changes direction? Let's look at this simple example where object changes direction by reversing along the same line. So it starts from here, initial position is positive 1 meter, and it goes all the way here, reverses back and arrives back here, and that is the final position because that's where we are making this measurement. So our final position is positive 3 meter. And remember, I'm still assuming the right is positive. So that's why the positive sign for all the position that are pointing to the right. See, this is still to the right from the origin, just like this one. So that's why both initial and final position have positive sign. Now we are ready to compute the displacement delta x using this formula. Final position minus initial position. By replacing the positions with value with proper sign, in this case, positive 3 for the final position and positive 1 for the initial position. And I am simply copying the negative sign. Thus, the displacement is positive 2 meters. But positive means right based on our coordinate system we chose. Remember, right is positive. So that means this positive means right. So we write something like this, 2 meters to the right. As you can see from this formula of the displacement, it does not have information on what happens in between the initial and final position. There is no information about this going here and coming back. No matter how far to the right it went from the final position before coming back to this position, the displacement is same as long as initial position and final positions are same. So in between information is not relevant to calculate displacement. What is the distance in this case? Remember, distance is path length. So based on that, can you answer this question? Is it still 2 meters, more than 2 meters, or less than 2 meters? Let's look at this, and it is your turn. Everything is same, only different is that now I am assuming to the right as a negative. So what happened? Initial position is negative 1 meter because it's being to the right, and right being negative, it has a negative sign. Similarly, the final position is also negative now because, again, we are choosing right as negative. That's our coordinate. Displacement is still the arrow that starts from initial position and goes to the final position, and can be computed or calculated by using the same formula. Now you go ahead, pause the video, and compute the displacement. What is your answer? The correct answer is B. or negative 2 meters. When written as a real direction, it means again 2 meters to the right, which is same as the previous answer when we chose positive to the right. Moving on to the velocity and speed using the example from previous slide. To compute velocity or speed, we need time information. I'm assuming the time the object takes to go from initial position to the final position is 2 seconds. So I randomly came up with this number. We define velocity as a displacement over time. So we have displacement, and what is velocity? It is displacement divided by time interval. We already know displacement, which is negative 2 meters from the previous slide. Therefore, let's use it. We also assumed the time interval delta is 2 seconds. Thus, the ratio becomes negative 1 meter per second. Delta x is negative 2 meters, and delta t is 2 seconds. 2 and 2 cancels, leaving negative 1 as the ratio and meter per second. Meter per second is the unit of speed or velocity. Now we need to write the physical direction for the negative sign. Here I am assuming negative is to the east. Rather than saying right, I am saying to the east. So we can represent any physical direction using either positive or negative sign. When we choose negative as east, positive automatically becomes opposite of east, which is west. The velocity is 1 meter per second to the east. Now let's define speed and compute it. Speed is defined as simply distance divided by time interval. We already learned how to compute distance. We simply compute the path length. So in this case, let's say the object goes all the way here 1 meter far from the final position before coming back to this final position. So that means the distance traveled while going from here and back here is 2 meters plus 1 meter plus 1 meter. So that is 4 meters. So distance is 4 meters. And distance is always positive or no sign for it. Okay? So time interval is still 2 seconds because it took just 2 seconds to travel all this path. So distance 4 meters, time interval 2 seconds. Therefore, the speed is 2 meters per second. You can see velocity is 1 meter per second to the east. However, speed in this case is 2 meters per second. You can see the speed is not simply the value of velocity in this case. When an object does not reverse the direction, just keeps moving in one direction, in that case, value of velocity is same as speed. But when it reverses, that's not the case. So let's keep that in mind. Thus, the speed is not always the value of the velocity, and speed does not have direction. So there is no sign or always positive sign. And these are also known as average velocity and average speed because we computed these values over 2 seconds time interval. The speedometer in your car shows the speed at that moment, not the average speed. The speedometer computes the speed during very short time interval and instantly displays it. The speed calculated in very short time interval is called instantaneous speed. For those of you who is familiar with the concept of limit and derivative, the average speed becomes instantaneous speed when time goes to the zero limit. Well, folks, congratulations on making this far. If you want to see if you learned it, try this question in another slide. The correct answer is C. Or is it? Find out using the formula and have fun.